the last lesson, we discussed how to calculate the area bounded by the graphs of two functions. In this lesson, we will see how this area can be revolved about the x-axis or y-axis to generate a solid. Now, for example, can you visualize an area like this sitting on the x-axis, and if you revolve it about the x-axis, what kind of solid do you generate? Well, I'm not doing a good job revolving it, but you can visualize. If I take that area and revolve it about the x-axis, I will generate something like a disk. Is that right? Yes, this is the axis. And what I have been doing is to revolve something like this to generate that disk. Well, we can take any given area. For example, look at this area. What kind of shape of a solid that we generate by revolving this about the x-axis? Now, if you revolve it about the x-axis, you will generate a solid. What will it look like? Can you visualize? Now, what kind of a solid do we generate if I revolve this area about the x-axis? And you should be able to visualize that. What kind of a solid that we generate? We generate something like this. Is that right? Yes. Okay. Now tell me, try and draw this. What kind of solid do I generate if I revolve this area about the x-axis? Is it something like a cone? Well, okay. I'm going to show you a weird surface, and I want you to try and draw a diagram and see how the shape of the solid will look if I revolve this about the x-axis. Well, we not only revolve about the x-axis, you can also revolve about the y-axis. Now, you must understand that the normal way of representing function, now this height here is generally called y. Is that right? This is y, which is the function value. Now, if the function graph is like this, in other words, this is the graph of a function of y, then this distance will be x. The distance of a function graph from the y-axis is x. The distance of a function graph from the x-axis is y. Very important to know that. Okay. Now, consider the graph of a function f of x. Now, here is the graph of a function. Now, this is f of x. All right. Now, the area enclosed by this graph is shaded. If this area is revolved about the x-axis, can you visualize the shape of the solid generated? I just showed you a couple of examples. In fact, this is very close to that. If you revolve this area about the x-axis, can you visualize the shape of the solid? I think that should be simple. Is that right? All right. If you can see this, the solid generated will look almost like this. All right. The purpose of this lesson is to calculate the volume of such solids generated by revolving a given area either about the x-axis or about the y-axis. Now consider a small strip of area dA. Now we go back and look at the same area. We're going to revolve this area. This is the graph of f of x, and we need to find the area, we need to find the volume of the solid generated when this area is revolved about the x-axis. in order to do that, we take a small strip of that area. In other words, this is the whole area. So what I'm going to do is, I'm going to cut a small strip. All right? There is the strip. Now, we are going to say that the width of this strip, that is this, the width of the strip is dx. And what is the length of the strip? Remember, the length of the strip is the distance of the graph from the x-axis. That will be therefore y. Y means f of x. So the length of the strip is the function value. Now remember, you take a point on the function graph. The ordered pair will be x, y, where y is the function value. So the distance of the graph measured from the x-axis is the value of the function, f of x. Similarly, the distance of the function measured from the y-axis is the function value, where the function is a function of y. All right, so consider a small strip of area dA. Now this is dA, this area is dA. Now the width of that is dx. Now that dx is actually very small. Now what is the height of this strip of area dA? We just talked about it. What is the height of this? The height of that will be, now in other words, you must be careful here. Now this height is this function value here. And this height is the function value here. That may not be the same in most cases. But because the strip is so small, the strip is so narrow, you can imagine that the length on the left and the length on the right are the same. That's the approximation that we take. But the approximation will be good because the width of the strip is very, very small, like a hair. All right. Now, so we got the height of the strip will be f of x. That's right. Now tell me, what is f of x multiplied by dx? So the height of dA is f of x. Now, I was asking you, what is dx multiplied by f of x? Actually, that is that area dA. All right. Now, what is the result if this area is revolved about the x-axis? In other words, I have the x-axis here, and the strip is right in here. Well, I made it very small, so it's not very visible. And what happens if I revolve with this about the x-axis? Well, I will produce a disk like this. Can you visualize that? Yes. So what we obtain by revolving this strip of area about the x-axis is that we produce a disk with the x-axis as its center. So the center of the disk will be the x-axis. There you got it. So you got a disk with its center at the x-axis. Now, if you do it on the y-axis, it will be a disk with the y-axis at the center. We will come to that a little later. Now, the disk will look like this. That is the disk, and that is the x-axis. And what is this height? The distance from the x-axis to the top of the disk will be f of x. That's right. Now, the thickness of this disk, what is the thickness of this disk? It's the same as this dx. All right, what is the radius of the disk? Now, the radius of the disk will be the length of that strip, isn't it? When this is revolved about the x-axis, this will become the radius. So the radius of the disk is actually the length of the strip, which is f of x. Okay, I hope you're following this. I want you to understand this, each of the steps that I'm talking about. So you got the radius of the disk is f of x, the thickness of the disk is dx. Okay. Now, if we call the volume of this disk as dV, can you tell me how to find the volume of a disk like this? Now remember, this is a circle, is that right? So, if you take the area of one face and multiply it with the thickness, that will give you the volume of this disk. Now, the one face of the disk is a circle. What is the area of his circle? Area of his circle is pi r squared, where r in this case is f of x. That's right. So, pi r squared is the area of this face, multiplied with the thickness of the disk. I'll give you the volume of the disk. And we're going to call the volume of the disk as dV. So if dV is the volume of the disk, then dV equal to pi r squared dx, where r is the radius of the disk. That means I can replace this r by f of x. That's right. So that will be pi times f of x squared dx. Now, such areas dA can be taken anywhere on the curve on the x-axis. Now, I took that dA here. I can take the dA over here. I can take it over here. I can take it anywhere I want, anywhere along the x-axis. That's right. So I can have a dA here, another dA here, another dA here, another one here. So look at that. But then you will say, aren't we wasting a lot of space? So we are not going to get an accurate result. Well, it looks like we are wasting a lot of space because I drew the width of the dA to be considerably large. Now, remember, in calculus, the width, that dx is very small, probably even smaller than the width of a hair. So, there are thousands of these strips, and each of them having a very small thickness. That means that dx is very small. Alright, now you can actually produce such disk by revolving each of these area about the x-axis. Is that right? Each of this area can be revolved about the x-axis, producing disks like this. But the radius of each disk will be different. Why? Because the height of the disk will be different as you move to the right. So, if you revolve this, you produce that disk. If you revolve this about the x-axis, you produce this disk. If you revolve this, you produce that disk. And so on. You can see each of these revolved about the x-axis will produce a separate disk. That means if you can find the volumes of each of these disks and add them all together, what you are obtaining is the total volume of the solid generated when that, well, I cut this into pieces. So now when you add the volumes of all these dVs, dV1 plus dV2 plus dV3 plus dV4 and so on, there may be thousands of these. You add them all together, you will get the total volume of the solid generated when this area is revolved about the x-axis. And isn't that a beautiful method? In fact, that is the method of calculus. And what do you call the process of adding all these volumes? Adding all these quantities is what we call integration. So we are going to use the method of integration. So each of these areas, when revolved about the x-axis, produces a disk of radius fx, f of x. Remember that f of x is different in each case because